In this video, we're going to look at percent change in volume and surface area. So if you haven't already, what I'd like you to do is read through this introduction to section 2.3, all on this first page, all the way down to activity 1. So if you haven't done that already, please pause the video and read through this introduction. All right, so hopefully what you got out of this was a motivation for something called similar figures. Similar figures have the same shape, but not necessarily the same size. So one way I like to think about similar figures is taking something like this to the copy machine and scaling it up, telling the copy machine to enlarge it. And then the copy machine will spit out pretty much the same thing, but bigger. And you could also do that in Word or other programs where you choose something and then drag a corner and make it bigger, where it's locking the ratio in so it's not distorting it and creating a larger copy. And that's called a scaled copy. And how many times bigger the sides are is called the scale factor. So the corresponding sides of two similar figures are proportional, and the common ratio of any two corresponding sides is called the scaling factor. And we're going to look at how that affects area in this activity. So question number 1 in activity 1 says, consider the following figure, which is this figure right here. Each box in the grid has dimensions 1 centimeter by 1 centimeter, and the slanted sides have length of about 2.83 centimeters. Okay, so we know area-wise then this is 1 centimeter here, this is 1 centimeter. So the area of one of these squares is 1 square centimeter. And we can count the centimeters to figure out the perimeter and area, and we can count the square centimeters to figure out the area. Now for the perimeter, since we have this distance, the diagonal of the square is not 1. It's actually more than 1. It's about 1.4. 1 is the distance of one of the sides of the square. So they told us then that this distance of this slanted side was 2.83, so we could use that to figure out the perimeter. All right, so I'd like you to pause the video and figure out the perimeter and area of this figure and start it when you're done. All right, well, for perimeter, what we're going to want to do is count the centimeters around the outside of the figure. So pick a starting spot and just count along the outside here, the boundary. So there's 1. That's kind of chunky. Let's make that a little bit smaller. Okay, so there's 1, 2, 3, 4, 5, 6. Maybe you could even write down the lengths of each of these sides. And that's the other side here is 1, 2, 3, 4. Okay, and then we have our 2 slanted sides. Both of those are 2.83 centimeters. This is also 2.83 centimeters. Oh, I forgot one. Do you see it? Right here. That's 1. That's 1, and that's 1. So let's put those down. That's 1 centimeter and 1 centimeter. And then lastly, we have this side over here, which is 4 centimeters. Now we're just going to add all those up. So we have 4 plus 6 plus 4 plus 1 plus 2.83 plus 2.83 plus 1 centimeters. And that adds up to 21.66 centimeters. All right, now we want to find the area. So now what we're counting are the number of squares. So this square is 1. Right? That's 1 square centimeter. So let's count these up here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then 25, 26. Then these two will go together to make 27. And these two will go together to make 28. Now you may have done that a different way, which is fine, but no matter how you do it, you should come up with 28 square centimeters. So now what you're going to do down here is you're going to draw a scaled copy of this figure with a scale factor of 3. So what that means is that every side is going to be 3 times longer. The sides are going to be 3 times longer. Kind of erase this here. So this side is 4, this side is 6, this side is 4. So when you start your drawing, it says to plan ahead so it fits on the paper. Maybe start in one of these corners down here. I'm not going to draw this whole thing for you, but I am going to have you do it. And so instead of going up 4, since we are doing a scale copy with a scale factor of 3, we're going to want to make this side 4 times 3 centimeters, or 12. And then we're going to want to make this side 6 times 3, or 18. So let's start, oh shoot, let's just start way down here even. Okay, so if we go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right there. Make sure I count that. I have to grab a different pen when I do this for you to see my cursor. So then you'll draw a line from your starting point up 12 units, and that'll be the side of your shape. All right, and then you're going to draw a line from here to here, and that'll be the base of your shape. And I'll just input a line there so I don't have to try to draw it straight. Maybe you'll use a ruler. Okay, so there's the start of it, and I want you to finish it. I want you to finish the shape so everything's 3 times, all the sides are 3 times longer. Now when you get to this part, that's 2.83, another way to think about this, instead of thinking about it as 2.83, you could think about whatever this distance is. Oh, let's use green. Whatever this distance is here, let's call it a diagonal distance. In your new shape down here, that diagonal distance is going to be 3 times as long. All right, so it looks like it's crossing 2 diagonals in the original figure here, right? 1, 2. So in my new figure, I'm going to want to cross 6 diagonals. Wherever you end up, you're going to go, there's 1, 2, 3, 4, 5, 6. It's going to have to be that long. That would be 3 times as long. So that's one way to deal with that scale factor there. So after you do that, after you get your picture all drawn down here, then I want you to find the perimeter and the area of those figures. Okay? And we'll come back and talk about this in a second, but pause the video and go ahead and complete that. All right, we're going to come back to that, but I want to skip ahead to number 2 here. And here we have 2 rectangles, and these rectangles are similar. Now, how do we know that they're similar? Well, if they're similar, that means that there's a scale factor involved in multiplying the old width to get the new width, and the old length to get the new length. In other words, that these sides are proportional to each other. So the ratio 6 to 2 is equivalent to the ratio 12 to 4. They're proportional. And if we divide those, we get 3. So that means that each of these lengths was multiplied by 3. So it has a scale factor of 3. Now, just a word of caution here. In the directions, it said the rectangle on the left is the original and the rectangle on the right is the copy. So this was the original and this was the copy. So you're always going to take the original multiplied by your scale factor to get the copy. But what if it was the other way around? Now we're not going to, I'm going to go back to the way it was, but this could happen to you in the future. What if this was the original and this was the copy? Well, now you have to ask yourself, what would I have to multiply 6 by to get 2? And that's a number less than 1, right? So another way to get that is to do these ratios like we did over here, except you're going to take the ratio of the new side to the original, new side to the original. Those are, again, proportional, and the common ratio here is 1/3. So we would say, in this case, the copy is 1/3. The sides of the copy are 1/3 the sides of the original side. So it makes a difference which one's the original and which one's the copy in determining the scale factor. Okay, so keep that in mind. All right, so we'll go back to how it was. Just wanted to bring that up. So we'll call this the original and this the copy. So we have our scale factor of 3. All right, find the areas of each rectangle, then find the ratio of the areas of the two rectangles. What do you notice? Well, we know the ratios of the sides is 3. The ratio of the sides is 3. What about the ratio of the areas? Do you think that's going to be 3? Seems logical. Well, let's work it out and see what happens. So let's find the area of the original. The area of the original is 2 times 4, which is 8. The area of the copy is 6 times 12, which is 72. So if we want to find the ratio of the areas, we're going to take the area of the copy divided by the area of the original. 72 divided by 8 is 9. So this tells us that the copy is 9 times bigger than the original in area. Do you believe that? Look at these two rectangles up here. Does this one look like it has 9 times the area of this one? Well, let me help motivate that a little bit for you. Or let me help you visualize that a little bit. So let's take one of these rectangles. So here's a copy of one of these rectangles, and what if we start putting it in here? How many of these rectangles does it look like will fit inside here? Well, we could just keep copy pasting and see. Looks like we're going to be able to fit maybe 3 up this side in there. I might not have them exactly the right size. And maybe 3 going across this way. I mean, it makes sense if that distance is 4 across the bottom and this distance is 12, then we could fit 3 of those across the bottom and 3 of them up that way. I think I copied them a little too big. But you get the idea, right? You could fit 9 of them in here. That's 9 times the area. So that makes sense. Let's get rid of these. So that's kind of interesting that the sides are 3 times as big, but the area is 9 times as big. So down here it says divide up the scaled copy with horizontal and vertical cuts to illustrate the ratio of the area. So let's do it that way with some scaled cuts. So we could take this 12, this length of 12, and split it into 3 fours. All right, and we could take this 6 and split that into 3 twos. And then slice it. Maybe I'll put in some straight lines. All right, so slice it this way at 2. And then we could put another slice in there. And then we could do the same thing with some vertical slices. Put this down here and this up here. Oh, let's go straight up. And you can see that you're going to get 9 of these rectangles, right? That's pretty close. So this area right here is equivalent to this area. So there's 9 of those in there. All right, do parts A and B again, but take the rectangle on the right to be the original and the rectangle on the left to be the copy. All right, so we talked about that a second ago. So the scale factor, if we change the original, and if we swap the original and this, our scaling factor is going to be 1/3. I'm going to call that K. This is a common variable for that. I'm going to call that K. So now if I do the area, I'm going to switch these when I'm swapping it now. So now the area of the copy is 8. And the area of the original is 72. So that tells me the area of the copy is 1/9 the area of the original, which makes sense, right? This is 1/9 the area of this. All right, so let's go back to this one that you guys were doing before. Now, what you should have found when you did the area and the perimeter of this stuff down here, I'll tell you what you should have come up with. So the perimeter of this one should have come out to be exactly 3 times the original perimeter. The original perimeter was 21.66. The scale factor was 3. The new perimeter should come out to be 3 times the original, which is 64.98. The area should have come out to be 9 times the original area. Now you're supposed to get this by counting up all the little squares, which is a lot of counting, which is 252 square centimeters. And technically you wouldn't have to count all the little squares. You could, you know, like I could have done over here is just looked at this rectangle here and said, oh, that's a 4 by 6, so that's worth 24. Probably some of you did that, which is good. All right, that's a 4 by 6, so that's 24, 25, 26, and then these two, 27, 28. So hopefully you did something like that to get 252. But the point here is that with a scale factor of 3, the area was 9 times as big. Exactly the same situation over here. When we took the rectangle and we scaled it by a factor of 3, the area was 9 times as big. And that will always be the case. Now start thinking about what is the relationship between the scale factor. Now here we're using S for scale factor, so that's fine. We can use S. If the scale factor was 3, the ratio of the areas was 9. If the scale factor was a third, the ratio of the areas was 1/9. What's the relationship here between the scale factor and the ratio of the areas? Did you figure it out? Well, we're going to make a conjecture. Suppose we have two similar figures with a scale factor of S. Describe how to find the lengths and the area of the scaled copy from the lengths and areas of the original figure. The lengths of the scaled copy are found by multiplying the lengths of the original by S. By S, by whatever your scale factor is. Now, perimeter counts as a length. So when we say multiplying a length, it could be a length, a diagonal, a perimeter, any measure of length. The area of the scaled copy is found by multiplying the area of the original, not by S anymore. That didn't work. Not by 3 in this case. You have to multiply by S squared. S squared. Pretty neat. All right, so if I took this rectangle right here, and let's say I was going to draw a copy with a scale factor of 10. I'm not going to draw it, but if the sides lengths were 10 times bigger, 200, 400, then I would know the area of that copy would be 10 squared times bigger than the area of the original. Or the area of the copy divided by the area of the original is 100. Right? It's 10 squared times bigger in area. That's the moral of that story. All right, let's look at another problem here. Activity 2. An architect provides a client with the following living room floor plan. The client wants a bigger living room and tells the architect to increase the length and width of the living room by 20%. Find the dimensions of the living room after a 20% increase. Draw and label a diagram of the new, larger living room. All right, go ahead, pause the video and do that and use your multiplier. All right, let's see how you did. Well, if we want to increase by 20%, our multiplier is 120%, just like we learned previously. So our multiplier is 1.2, a 20% increase. A 20% increase is saying you're going to have the 100% you started with plus 20%, 120%. So we're going to multiply 22 by 1.2, and we're going to get 26.4 feet. And we're going to multiply 18 by 1.2, and we're going to get 21.6 feet. The client tells the architect they're happy with the 20% increase in dimensions because now they have 20% more floor space in the living room. Is the client correct about the increase in floor space? Well, to find the increase in floor space, we're going to have to find the area, right? That's the area. Let's find the area of these things. Now, let's think about what we just learned about area. Here, your scale factor is 1.2. Is the area of the new floor going to be 1.2 times bigger than the area of the old one? What did our conjecture say? The area of the scale copy is found by multiplying the area of the original by s squared, the scale factor squared, not just the scale factor. So, I don't know. This is looking a little fishy, about 20% increase. Let's go check it out by looking at the areas. So the area of the original is 22 times 18. 22 times 18 is 396 square feet. The area of the new floor space is 26.4 times 21.6, which is 570.24. So now there's two different ways that we can look at figuring out the percent increase. Remember last chapter we found percent increase by taking the amount of increase. So we're going to take the new amount minus the original amount divided by the original amount. Let's see what that gives us. So that's 174.24 out of 396. And then we get 0.44. So that is a 44% increase. Wow, do you think that's right? We only increased the sides by 20%, but the area increased by 44%. Well, let's think about, again, our conjecture. Our conjecture says the area of the scale copy is found by multiplying the area of the original by s squared. Let's try it that way. What if I took the area of the original times s squared, I'm supposed to get the area of the copy. So the area of the original was 396. S is 1.2 squared. Let's multiply that. 396 times 1.2 squared, look at that, is 570.24. 570.24. So what was our multiplier here? Our multiplier was s squared. That was our multiplier. Our multiplier was 1.2 squared. What is 1.2 squared? Let's check that out. That's 1.44, or 144%. So what percent increase is that? If you have a multiplier of 144%, that's a percent increase of 44%. That is what was added on to the 100%. All right, so we could have come up with the increase in the percent increase in floor space by simply doing s squared. That's kind of neat. All right, to find the percent increase in area, just do s squared, subtract off 100%, and that's your percent increase. Part C, does the increase in floor space align with your conjecture about how to find the area of a scale copy? Yes, it does. Our conjecture was that it was s squared, and that worked right here. We just did it. Okay, the client plans to cover the living room with carpet that costs $24 per square yard. Square yard. Remember, these are square feet. Okay, shoot. You got to think about square feet and square yards and feet. Find the cost to carpet the original living room and the cost to carpet the larger living room. Then find the percent increase in the cost in the carpet as a result of the 20% increase in dimensions of the living room. So I would like you to do this one on your own, and we will see how you did when you submit your work. Now keep in mind, that this is per square yard and your measurements are in feet or square feet. You could either do the feet or the square feet. So you could either convert these dimensions to yards first and then find the new area in yards, or you could convert this area into square yards. But be careful, it's not the same conversion factor. You remember, there are 3 feet in 1 yard. I'm not going to tell you what it is right here, but it's a different number than 3 for square feet in a square yard. I want you to think about it a little bit. All right, in the next video, we'll see what happens with volume when we increase the sides by a scale factor of s.